at a temperature of 25 degrees Celsius. What is the net force due to the nitrogen on one wall of the container? Okay. Compare the force to the sample's weight. Okay, so we're going to calculate the force that this gas exerts on a wall. If it is at 1 atmosphere, and the force is 15 pounds per square inch, right? And so we'll calculate first the pressure, and the force will be the pressure times area. Okay. So the force is pressure of the gas times the area. Let's call this L squared. Yeah. What is the pressure of the gas? It's N RT over V. So and V is LQ. So the force is nRT times divided by L. Okay, N is half a mole, R is gas constant, you know the temperature, and L is the volume. Okay, so volume to the power 1/3. All right, so let's calculate this. N is 0.5 moles. R is 8.314 joule per mole per Kelvin. Temperature is 298 Kelvin. And the volume is 2 liters, except that we got to make it in meter cube. That many meter cube to the power 1/3. And the force will work out in newtons. Okay? The moles cancel, Kelvin cancels. Joule divided by meter gives you newtons. All right, so let's do this. The force is so. So 2-liter bottle is 2-liter is that's 1 liter. So imagine the box is not that much bigger. So the box is like this. The force that the gas exerts on this face, on the face of the box, is 9,000 newtons, 10,000 newtons. Is that large? So your mass is 60 kgs times 10. Your weight is 600 newtons. The force is equal to 15 times your body weight. So you take a box of gas like that, the force on each wall is 15 times your body weight. And you shouldn't be surprised. Remember, the force on this guy due to atmospheric pressure was 1,500 pounds. Okay. They also ask you, compare the force to the sample's weight. Okay. So the sample's weight, the mass is the mass is the molar mass times the number of moles. Okay, the gas was, what is the gas? Nitrogen gas. So half a mole, and nitrogen is 14 grams per mole. No, 28 grams per mole. So it's 28 grams per mole. 14 grams. So the weight is mg, which is 14 into 10 to the minus 3 kgs times 10 meters per second squared. 2.14 newtons. So the weight of this gas is very small compared to the force that it's exerting on the walls. Okay. The force that it's exerting on the walls is 100,000 times greater than its weight. Okay. What is the gauge pressure in a 25 degrees Celsius car tire containing 3.6 moles of gas in a 30-liter volume? Okay, so pressure, and this is absolute pressure that you calculate. So nRT over V. 3.6 moles. R is 8.314. Temperature is 298 degree Kelvin. Volume is 30 liters. A liter is 10 to the minus 3 meter cube. Okay. So this will come to the top. That's so that is the pressure. Pascals is Newton per meter square. This is 1 atmosphere. So the pressure in the tires is 3 atmospheres. That's the absolute pressure. What's the pressure in your car tires? Huh? So let's say 30 psi. What is 1 atmosphere? 15 psi. 15. So the pressure in your tires is 2 atmospheres. But that is gauge pressure. So the gauge pressure is absolute pressure minus atmospheric pressure. Okay, so 2.97 times 10 to the 5 minus 1 times 10 to the 5. 1.97. Okay. There's the atmospheric pressure, that's 15 psi. 2 times 15 psi is 30 psi. Okay, so the pressure that you talk in your tires is really the gauge pressure. Okay. So if you want the absolute pressure in your tires, you would add 1 atmosphere to it. You would add 15 psi to it. Okay. What will the gauge pressure be if you add 1 liter of gas originally? So now you're filling your tires. Okay. And you're adding 1 liter of gas originally at atmospheric pressure and 20. What will be the gauge pressure? Okay, so now what we'll do is, what we are doing is, when you're adding air, you're increasing the number of moles and the pressure will increase in your tires. Okay. So we'll calculate how much the absolute pressure will increase, and I'll just show you, and then you can calculate the gauge pressure increase. Okay. So what we want to do is, so you're adding, when you go to a gas station and add air, you're adding, assuming you're adding gas at the same temperature and all that, but the compressor makes it hot. We'll ignore all of that. You're adding at the same temperature. Okay. So B, how many moles did you add? You add N is P times V. Okay. You added the moles at 5 pascals. what is the gauge pressure? Will be the gauge pressure if you add 1 liter of gas at atmospheric pressure and 25 degrees. So there you're adding this, and 1 liter is 10 to the minus 3 meter cube. R is 8.314 joules per mole per Kelvin. You're adding the gas at 25 degrees Celsius, 298 Kelvin. Okay, so when you added 1 liter of air at atmospheric pressure, you added this many moles of air. Okay, so now how many moles of air do you have? Originally you had 3.6 moles. Now you added 0.04 moles. So you have 3.64 moles of air now. And the pressure will increase. You replace this by 3.64. Okay. So it increased by 1% is what happened. See, the new pressure is N nu, the number of moles, RT divided by V. And we'll assume that, assuming the temperature remains constant and the volume remains constant. So when you add the air, it gets compressed and the volume of the tire didn't change, is what they're saying. So you would put R, temperature, volume, okay? So the new pressure will be, all you do is take this old pressure, this pressure, divide by 3.6 and multiply by 3.64. Okay. So the new pressure is 3.003 into 10. So after you added air, that's what the pressure increased. And then you want the gauge pressure, you just subtract 1 atmosphere. Okay. So the new gauge pressure will be just 2.003 atmospheres. Some incandescent light bulbs are filled with argon gas. Argon is noble gas. Okay, so it won't react. The filament will be at high temperature, and if you fill it with oxygen, it'll get oxidized. So you fill the bulbs with inert gas, something that it won't react with. What is the VRMS of argon atoms near the filament, assuming the temperature of the filament is 2500 degree Kelvin? So that incandescent bulb, that filament that's glowing, is at 2500 degree Kelvin. Okay. So here are the VRMS speed formula. 3 kT T over M. And okay, so the root mean square velocity of a molecule is 3 kT over m. In this formula, this is the mass of a single atom or molecule, and you can multiply this by Avogadro's number and that by Avogadro's number, and that becomes R, and then that becomes molar mass. So this is also equal to 3 times RT over molar mass. Okay. You can find the mass of a single molecule, but this is easier to do. What is the molar mass of argon? That red number, 40. Okay, 40 grams. So 3 times 8.314 joules per mole per Kelvin. The temperature of the argon gas near the filament is 2500 degree Kelvin, and the molar mass is 40 grams, that many kgs per mole. That mole cancels, the Kelvin cancels, and this square root of joules over kg will give you meters per second. Okay. So near the filament, this is the speed of the argon gas atoms. Okay. So let's do the following. We'll bring this to the top, make that 10 to the 3. Square root of that will give you 10 to the 3. So meters per second. 3 into 8.314 into 2.5 divided by 40. All right, so what is the average speed of the molecules in this room? I'm sorry?
500 meters.
500 meters, half a kilometer a second. Okay, and the molecular weight is 28. So argon is heavier, it's 40 grams per mole, and at that higher temperature, it's going at almost 3 times the speed. Okay. So this problem says the partial pressure of carbon dioxide in the lungs is 470 pascals. Okay, what is atmospheric pressure? 10 to the power 5 pascals. 1% of that would be 1,000 pascals. Okay, this is 1 atmosphere. The partial pressure is 500 pascals, 0.5%. So 0.5% of the air in your lungs is carbon dioxide. That's what that number tells you. Okay. When the total pressure in the lungs is 1 atmosphere. What percentage of air molecules in the lungs is carbon dioxide? Okay. So the partial pressure is the number of the fraction of the molar fraction, the number of moles of carbon dioxide divided by the total times the total. Okay, so Ni over N total, that gives you the fraction of is Pi over P total. 470 pascals 10 to the and so the percentage Ni over N total if you want to find the percentage, you just multiply that by 100. So the partial pressure of carbon dioxide in the lungs about when the total pressure is what, okay. Compare your result to the percentage of carbon dioxide in the atmosphere. So in the atmosphere, it's 0.033%. Okay. Okay. So what has happened is here's why you calculate all this stuff. Okay. Here's blood, and what is the function of blood? It goes to the lungs, and here is carbon dioxide. You don't like my carbon dioxide molecules? All right. Here's oxygen molecules. Here's an alveoli. What is the job of blood? You want to get rid of the toxins, carbon dioxide, and you want to bring in oxygen. Diffusion happens from a higher concentration to lower concentration. Okay, so for diffusion to happen, so oxygen concentration should be higher. And remember, in normal air, the concentration of carbon dioxide is 0.033. Okay, so when there's lower concentration of carbon dioxide will go here, oxygen will go there, and then you can breathe out. Okay, so the carbon dioxide percentage increased from 0.033% to 0.47% after you exchange air, carbon dioxide. Okay, so. All right. How much heat must be added to raise the temperature of 1.45 moles of air from 25 degrees to 33 degrees at constant volume? Assuming air is completely diatomic, repeat the problem for the same number of moles of xenon. Okay. So for part A, CV at constant volume, CV is F by 2R. Okay. At room temperatures, so this is room temperature from 25. At these temperatures, air, which is a diatomic molecule, the number of degrees of freedom is 5. Okay, so at room temperature. CV equal to N is 1.5 moles, CV is 5 halves. I'm not putting units now. 8.314, and delta T is 8 degrees Celsius difference. Okay.
Do we not have to change it to Kelvin for this one?
All right. So no, you don't have to be sorry on that one. Difference in temperature in Kelvin and Celsius is the same. You're adding 273.
Oh, okay.
No. right? Okay, so you have to add 250 49.4 joules. Okay, at constant volume to warm it by 8 degrees. Okay, what is xenon? What is the difference now? Where is xenon on the periodic table?
It's a noble gas.
Hmm?
It's a noble gas.
Mm-hmm. Okay, so what changed?
The mass and the type of particles or shape of it. Degrees of freedom.
The degrees of freedom. F is 3 now. Okay. So CV, okay. F is 3, CV is 3/2 R. And now, so since the number of degrees of freedom, since your spending habits are more conservative, it doesn't need as much heat. Okay, so you divide that by 5 and multiply by 3. Okay, so to heat xenon, all you need is 149.7 joules. See, lower the degrees of freedom, less energy you need to. So to warm air by 8 degrees Celsius, you needed 250 joules of heat. To warm xenon, all you needed was 150. Okay. All right, using the approximation, so what this is telling you is, what is the area of this column? It's just the value of this function times the width of this column. This is almost rectangular, so the height of the rectangle times the width of the rectangle. Okay, so the area under this curve is just the height times the width. So that's what they're saying. So in doing the integral from V1 to V1 plus delta, in doing the integral from V1 to V1 plus delta, it's just the height times the width. Okay, height of the column times the width. For small, we estimate the fraction of nitrogen molecules at a temperature of 300 degree Kelvin that have speeds between 290 and 291 meters per second. Okay, so all you have to do is the fraction, they're asking you for the fraction. So the fraction was the fraction is this many molecules divided by the total molecules. So you just have to take this is the probability. Okay, so this would be the value of the function 4 pi m over 2 pi k t 3/2. All right, so this would be the fraction of nitrogen molecules. So for instance, this will give you the fraction of nitrogen molecules at speeds between 290 meters per second and 291 meters per second in this room. What is the average speed of those molecules in this room? 500 meters per second. Okay, so the average speed is about 500 meters per second. This will give you how many molecules have a speed of between 290 and 291. Okay, so what all would you need? The temperature is 300 degree Kelvin. The Boltzmann's constant is 1.38 into 10 to the minus 23 joules per Kelvin. V is 290 meters per second. And this is the mass. Okay, so what we'll do is m over k we'll write as m over r. Okay, you can multiply this by Avogadro's number, multiply this by Avogadro's number, and okay, so m over k will replace that by that, and that will be molar mass is what is it, nitrogen 28 grams per mole divided by 8.314 joules per mole per Kelvin. Okay, so now you have everything in there to calculate that. Okay, to calculate this expression. Delta V is 1 meters per second. Okay, and you can calculate that. So what do you expect for this number to be? Probably less than 1%. Okay, so the fraction would be, it will probably be less than 0.01. Okay, so that's what that number should come out to. Okay, but that'll tell you how many molecules in this room have speeds between 290 and 91 meters per second. Okay, so that's a real calculation. Okay, you want me to do it, or you guys can do it? Okay, put all those things. Yes? No? Well, it'll, yeah. I know I got 10 more minutes, 9 more minutes. In deep space between galaxies, the density of molecules, which are mostly single atoms, so between galaxies, they're all single atoms, can be as low as 10 to the power of 6 atoms per meter cube. So here in this room, in this volume, the number of atoms is about 10 to the 26. There's 100 moles in here. 10 to the 26 molecules. In deep space, it's 10 to the 6 atoms. And the pressure is a frigid temperature is a frigid 2.7 K. What is the pressure? Okay, I'm just going to do part A, okay? We'll just do part A. So pressure is N K T over V. And you have N over V is given, KT. So in interstellar space, we are calculating the pressure. This is 10 to the 6 per meter cube. K is 1.38 into 10 to the minus 23 joules per Kelvin. Temperature is 2.7 Kelvin. Pascals. 10 to the power of 5 pascals. Okay, so let me write it like this. 3.73 into 10 to the minus 22 into 10 to the 5 pascals. Why did I write it like that? This is 1 atmosphere. So 10 billion trillionth of an atmosphere. Okay. That is the pressure in interstellar space. Okay, one more problem. The air inside a hot air balloon has a temperature of 370 degree Kelvin. What is the temperature in this room? 300 degree Kelvin. Okay, so you're increasing in a hot air balloon, you're increasing the temperature by 20%. And then that, so what happens? Pressure is N over V kT. Okay. What is the pressure of the air in the hot air balloon? 1 atmosphere. Okay. So if you increase the temperature, the density decreases. When the density decreases, if you're less dense than the surrounding air, then you'll rise. Okay, so that's the idea of the hot air balloon. As a temperature of that and a pressure of 100, this is 1 atmosphere. Okay. The same as that of air outside. Using the composition of air as that, find the density of air inside the balloon. Okay. Okay, so the density. N is no, we'll do this. This gives you the number of moles, molar density. Okay. And so this is the molar mass equal to P and okay. So we're going to take 1 mole, 1 mole, and that will be the molar mass. So the molar mass, well, you have to calculate the average molar mass. It's 78% nitrogen, so it's 0.78 into 28, and 21% oxygen, 32, plus 1% argon. Argon is 40 grams per mole. So you have to calculate that mean value. So 28.96 grams per mole. That's the molar mass of air, the weighted average. Okay. So we'll take 1 mole of this. We'll talk about 1 mole. Okay, find the density of air inside the balloon. Okay, so the density is, okay, so 1 mole, 28.96 into 10 to the minus 3 kgs per mole. Volume 1 meter cube equal to pressure is 1 atmosphere. They say, okay, 101 kilopascals. So. Molar mass is 28.96. So this M cap, well, okay. All right, we just have to calculate this. I don't need to write that. And the temperature is 370 Kelvin. So, okay. And pascals is Newton meter square, which is so what we need for density, kg per meter cube. Pascal is Newton per meter square, and joule is Newton meter. So the Newton cancels and the meter cube, you get kg per meter cube. Okay, so the units work out. All right, so this is the density. The density in the hot air balloon is where did I go wrong? So pressure is that. Okay, so the density of air is about 1.3 kgs per meter cube. So this density should work out less than that in the hot air balloon, okay? I did a mistake someplace. All right, I will post the corrected solution, okay? All right.